So today we have Dorje Brody. He speaks about the evolution of speed of open quantum systems, or dynamics, actually. Go ahead.
Okay, thank you very much, Andres. Thank you for the organization and the invitation. Right, so my talk today is going to be about evolution speed of open quantum system. It's based on a joint paper published recently with Bradley Longstaff, and it's to do with how fast a given quantum state can move. Why would this be of any interest? Well, the answer is that in implementing quantum technologies, for example, in quantum computation, if we know how fast a quantum state can be manipulated, then that in turn tells us the limit of this computational power, if you like. Okay, so that's the idea. But in particular, I'll be interested in evolution speed of PT-symmetric quantum systems. And I see many of the usual suspects in the list of participants, but I don't want to assume everyone is familiar with PT-symmetric quantum mechanics. So I just want to start out with a brief history, not all the aspects of PT-symmetric quantum mechanics, but some aspects that are relevant to motivate this talk. So the idea of our current interest in PT symmetry goes back to a paper from 1998 by Bender and Becher, who observed that if you have an operator, an observable, say Hamiltonian, that is invariant under PT conjugation, if you commute it with PT, then the eigenvalues can be entirely real. In particular, if the eigenfunctions of the operator are also eigenfunctions of the PT, then the eigenvalues are real. Otherwise, they come in complex conjugate pairs. Now, this was an interesting observation, and the question naturally came up as to whether one can do quantum mechanics with an operator of that type. And this wasn't immediately obvious for the following reason, namely, if we have a Hilbert space equipped with Hermitian conjugation, as in standard quantum mechanics, then that determines the inner product and also determines the adjoint. Whereas if you want to replace that with a PT conjugation to determine inner product,
Hello.
Yes, then the parity operator, being Hermitian, squares to 1 and trace being 0, the eigenvalues of the parity operator plus 1s and minus 1s come in the same number. And therefore, the inner product becomes indefinite. So this was viewed as a problem until 2002, when two papers were published, one by Bender and his collaborators, Jones and I, and the other one by Ali Mustafazadeh, both of which showed in essence that if you have a PT-symmetric Hamiltonian, then there exists another operator, let's call it C, that commutes with the Hamiltonian with the property that the eigenfunctions, so eigenvalues of the C operator, plus 1 if the parity type of the eigenstate is positive, and minus 1 if the parity type is negative. And since C commutes with Hamiltonian, PT conjugation is equivalent to CPT conjugation. So Hamiltonian becomes CPT invariance, and you can use CPT to define the conjugation operation and therefore the inner product, and then you get positive definite inner product. So you can restore the probability interpretation of quantum mechanics. So this gave a way forward, and in particular, the product CP is a Hermitian and positive operator. So CP, the operator CP can be viewed as defining a metric in this Hilbert space. Okay, and the question, and in particular, the square root of CP can be used to transform between a Hermitian operator and PT symmetric operator, and you can go back and forth. And that leads to the question whether PT-symmetric quantum mechanics is equivalent to Hermitian quantum mechanics. Now, Mustafa Zadeh from early on have often argued that the answer is yes, they're entirely equivalent because there exists an isometric map between the two Hilbert spaces. But the situation is in fact a little more complicated for several reasons. For instance, the degrees of freedom of a PT-symmetric Hamiltonian is larger than that of a Hermitian operator. And also, PT-symmetric operator can admit these phase transitions. That is to say, if you change the parameters in the Hamiltonian, then it can be that the PT-symmetry of the eigenfunctions gets broken and eigenvalues turn into complex conjugate pairs. And that cannot happen with Hermitian Hamiltonian. So what is going on here? And in 2014, I was able to give a partial answer to this question, where I found a way to construct a PT-symmetric Hamiltonian in such a way that the degrees of freedom in Hamiltonian associated with the metric operator Cp and the remaining degrees of freedom can be isolated. And it turns out that the remaining degrees of freedom are exactly the same as the degrees of freedom in a Hermitian operator. And furthermore, the degrees of freedom associated with the metric operator, or Cp if you like, turns out to be not physically accessible. That is to say, one can show that there are no experiments in which one can adjust any of these parameters, and likewise, there are no observable for which one can estimate the value of these parameters. So the metric operator is not something one comes into the experiment. So it's not physical, basically. And therefore, in the case of finite dimensional Hilbert space, indeed, it is the case that PT-symmetric quantum mechanics and Hermitian quantum mechanics are equivalent. The situation changes quite a lot in the case of infinite dimensional Hilbert spaces. And the reason is because the domain of the operator Cp and the domain of the Hamiltonian need not coincide. And therefore, some of the states can be thrown out of Hilbert space when you transform from one to the other, and one can't really say anything about the equivalence of the eigenvalues either. So this is very much sort of open question. So that's all to do with PT-symmetric quantum theory in the context of closed systems. But backtracking slightly, going back to around 2007, people started to make the observation that you can realize or implement PT symmetry in the lab by means of balancing gain and loss. So the idea itself is a simple one. Imagine you have a system, and on the left-hand side, you pump energy in. On the right-hand side, you drain energy out. Now, if you apply the parity reversal, then gain becomes the loss and loss becomes the gain. But if you now also reverse things in time, then you restore the original configuration, or what appears to be the original configuration. So, and therefore, you can implement PT symmetry in the lab, and that caught a lot of interest, leading to all sorts of experiments being performed, starting with optics, and there are many other experiments in which interesting effects have been observed for open systems. Now, the majority of these experiments, however, are concerned with classical systems for which either the evolution in time or in space can be represented by means of a Schrödinger equation associated with a PT symmetric Hamiltonian. What about manifestly quantum mechanical open system for which you balance gain and loss, where it turns out that you can't have an exact PT symmetry in this particular sense of balancing gain and loss. The reason being that, let's say if I were to required to, let's say, pump 10 electron volt of energy into the system in 20 minutes time, then I need to have a precision of both time and energy, which violates the uncertainty principle in quantum mechanics. Putting the matter differently, to manipulate the energy or maybe particle number of a system in quantum mechanics requires things like absorption, emission, tunneling, etc. And all of these one can't control with precise, with high level of time precision. And therefore, one has to look more closely into open system dynamics. So that takes me to the next topic. So open system dynamics, what do I mean by that? Where I have in mind a system called that S, which is coupled to another system B. I use B having a bath in mind, but B can be as small as one particle, it doesn't matter. So the total system S plus B may be represented or described by a pure state wave function, let's say capital psi. However, if you're talking about the system itself, then the state of the system is determined by tracing out the environment B. And therefore you form a projection operator onto that pure state wave function, and then you trace out the environment, and the result is a density matrix, which is not going to be a pure state. So rho s square is not equal to rho s. Now the tracing out of the environment may seem somewhat abstract if you're not familiar with this kind of description, but it's fairly straightforward. So let's take an example where the system and bath are both spin 1/2 particles. And let's say you have a system prepared in a spin 0 singlet state. And the tracing out of B then amounts to measuring the spin of B without keeping the record. That's the essence. And therefore, if the spin measurement of B is up or down, so let's say B is down, then the system is up. If it's down, then the system, so if it's up, then the system is down. Okay, so you get this mixed state density matrix given in this form. Now, just as a side remark, this is not to be confused with a coherent superposition of up and down, which one can experimentally distinguish these two states. Okay, so we have a mixed state and not a pure state. Okay, now density matrix can be thought of as describing a classical average over the space of wave functions. So basically, it represents our lack of knowledge of the state. Okay, so you may have some probability distribution over the wave function, and you form the projection operator to the wave function, and then you average over, and that gives you the density matrix. But the map from the probability distribution of wave function to the density matrix is uncountably many to 1. So given a density matrix, there's no way of determining what kind of mixture it comes from. Okay, so that's a mixed state. Now, how does mixed state evolve in an open environment? Where the answer has been known for long, and it's given by this differential equation, the so-called GKLS, or Lindblad equation for short, where the first term with H is the usual unitary term, and then we have these Lindblad operators. There are one or maybe many, L, which may or may not even be Hermitian, which characterizes the way in which the system interacts with its environment. And this equation has a long history. So the first time the equation was written down was in fact by Landau in 1927, it turns out. So Schrödinger's paper, I think, appeared in 1926. And then in 1927, everyone knows that von Neumann introduced the idea of density matrix. But in fact, in the same year, what is perhaps less known, is that Landau also introduced the idea of density matrix, and then he wrote down the dynamical equation for the density matrix, which is what we call today Limblett equation, where the Limblett operator is the annihilation operator. So this form of the equation has been known for a long time. I think that the contribution of Gorini, Paskowski, Sudarshan, and also by Limblett is to prove that if you demand that the density matrix obeys a deterministic differential equation, and the trace of the density matrix remains 1, and the eigenvalues of ρ are positive, then it is necessarily expressed in this form and no other form which admit these properties. Okay, so that's the dynamical equation of density matrix in an open environment. Now, given that this is a linear equation in the density matrix, you can think of this as the time derivative of ρ equals to an operator, Liouville operator, acting on ρ. You can formally write in that way. I'll come back to more details about this later. But it turns out that the eigenvalues of the Liouville operator, sometimes people in quantum information call this super operator. But anyway, the Liouville operator, the eigenvalues come either in real numbers or else they come in complex conjugate pairs. And therefore, in fact, every open quantum dynamics is, in a certain refined sense, PT symmetric. So that's something some people have known for several years now. Okay, so now switching topic again to discussing briefly the speed of evolution in the case of pure state in a Hermitian context. So to study the speed of the dynamics of the state, we write down what one might call the Schrödinger-Kibble equation, which is top equation up here. So the time derivative is given by minus I over h bar times h minus its average. We can call that E, if you like. H minus its average acting on psi. Now, this equation in Hilbert space is in fact a nonlinear equation because we have a cubic term on the right-hand side. On the other hand, along every unitary orbit, the expectation value of the energy Hamiltonian is constant. And therefore, it gives you standard unitary evolution along every orbit. And Kibble is the one in late 70s wrote down this equation for a number of reasons. But the primary to take out, to remove the so-called dynamical phase in time evolution. So you only accumulate the geometric phase, but not dynamical phase as the state evolves. And this also makes it clear, incidentally, that if you have a stationary state, then the left-hand side equals 0. So you get h psi equals e psi, the time-independent Schrödinger equation, without evoking the so-called correspondence principle. Anyway, so we take this equation and then we compute the square, and that gives us the squared velocity. And the factor of 4 is conventional. There's a long story to this 4 is the same 4 as the square of 1/2 in uncertainty relation, and it's also the same as the square of the radius of the Bloch sphere for spin 1/2 system in quantum mechanics. Excuse me. Anyway, so 4 is just a convention which appears in quantum mechanics. So that's the velocity. Alternative way of understanding this equation is to write down the velocity vector, which is the usual Schrödinger derivative of the state minus the component of the first derivative in the direction of the state. Okay, if you take out that component, that gives you proper velocity vector, and then you can use that to define velocity squared. In either way, from this representation, it becomes immediately apparent that if you take the square of that vector, then you have psi and the h minus its average squared psi. So that gives you the the uncertainty in the Hamiltonian, and this is known as the Anand and Aharonov relation, that the squared velocity of the state is given. So what about a mixed state? Before I dive into my topic, one more background topic. So, and in the case of mixed state, let me look at the unitary evolution first, just for comparison with the previous pure state discussion, the Anand-Aharonov relation. So in the case of mixed state, things are a lot more complicated and the different ways in which one can study. So in the most ideal world, one would like to work in Hilbert space. Now, backtracking slightly, when we talk about speed, of course, the speed depends crucially on the choice of the distance, okay? So depending on which space one is working with, the notion of speed would be different. So if we want to work in Hilbert space, as we did in the case of pure state up here, for mixed state, since the density matrix is like probability, we want to take the square root to get Hilbert space element. So let C be any Hermitian square root of the density matrix, so that C square equals rho. Okay. Then the velocity square would be given by 4 times the trace of C dot squared. And it's fairly easy to calculate this. And one finds that the speed turns out to be given by the trace of rho times h squared average, minus trace of h times square root of rho times h times square root of rho. Now this odd-looking expression, in fact, coincides with the energy variance if rho were pure state. That is to say, the trace of h root rho coincides with the square of the trace of rho h. Okay, so this quantity reduces to the Anand-Aharonov relation, but for mixed state, this quantity is less than the energy variance. And in fact, this is known quantity defined by Wigner and Janase back in the 60s, where they call this expression skew information. So it is the skew information which gives you the speed of evolution of mixed state in Hilbert space. Okay. Now, what about open system? Now, for open system, in the ideal world, what we would have liked is to start from a Limblad equation and then deduce the dynamical equation satisfied by the square root of the density matrix. And with that, we can work out the speed of evolution in Hilbert space. And we tried very hard, but we weren't able to deduce the right equation. Hopefully it does exist, but we don't know how to write that down. And therefore, we took an alternative approach. So rather than working in Hilbert space, we decided to work in the L1 space, or if you like, Euclidean space. Now, so the idea is as follows. If you take a density matrix, it turns out that density matrix occupies a certain region inside of a large Euclidean space, Rn square minus 1. And it's also an interior point of a sphere sitting inside that space. Not the whole of the sphere, but part of it. And this idea relies on certain results worked out by Hodge, mathematician Hodge back in the 50s. So it's a slightly complicated idea, but intuitively speaking, we can reinterpret this in a trivial way. Namely, if you have a density matrix, it's Hermitian, so it has got n square degrees of freedom, but the trace of rho equals 1, so you have n square minus 1 degrees of freedom. And that, and therefore you can think of the degrees of freedom of density matrix as given by an element of R n square minus 1. So that intuition is completely fine. So we are going to work out the speed of the evolution of the density matrix in this Euclidean space. So it will be slightly different from the Hilbert space notion, because notion of distance is now changed somewhat. And to study this, here's how we proceed. So we introduce an orthonormal basis for the linear space of operators on n-dimensional Hilbert space equipped with the trace inner product. So if we have any operator, sigma and tau, then the inner product is given by the trace of sigma dagger times tau. Okay, so we form an orthonormal frames, and there are exactly n square of those in a Hilbert space of dimension n, and we call them sigma 0 and sigma j's. Sigma 0 we take to be the trace part, so sigma 0 equals 1 over root n times the identity matrix, and then the remaining operators are trace free. Okay, so you can think about the Pauli matrices for 2 by 2 case. So sigma 0 would be proportional to the identity, and then sigmas are the 3 trace free Pauli matrices suitably normalized, and they satisfy the orthonormality condition given down here. Okay. So with this choice of basis elements, an arbitrary density matrix can be represented in the form down here, where the expansion coefficient, the R sub j, are given by, as usual, just the trace of rho dotted with sigma j. Okay, so that gives you the jth component of the vector. And in that way, we can translate the notion of density matrix into simply a vector in Euclidean space, albeit of a slightly larger dimension. Okay, so the next task would be to translate the Limblad equation for the dynamics of the density matrix into the dynamical equation satisfied by R. But before doing that, one other comment, sorry. So incidentally, for pure state, trace of rho square equals 1, but substituting this representation into the trace of rho square representation, one finds that indeed for pure state, we get a sphere of a radius 1 minus 1 over n. Okay. So for n equals 2, you get 1/2, which is the radius of the block sphere. Okay, so coming back, so we have this Limblad equation, and what we do is we substitute this representation into the Limblad equation, and that gives us a differential equation after a little bit of fiddling, a differential equation satisfied by the vector R, and naturally, since Limblad equation is linear in rho, the resulting equation would also be linear in R. And here is the result. So R dot is a vector B plus a matrix lambda acting on R, okay? Where the lambda matrix is given more specifically by this long expression here, and likewise the B vector is given as on the page, okay? And with that representation at hand, now the dynamical equation, we can look at the Louvre operator, and we can write down explicitly the matrix elements of the Louvre operator, the so-called super operator, and it's given by given as follows, where we can work it out, and here's the result. So essentially this lambda matrix gives you the component of the Louvre operator for ij not equal to 0, whereas the B vector is going to give you the 0th component of that large matrix. So in that way, we can translate the dynamical equation in terms of more familiar matrix form, but we can also talk about the eigenvalues of the Liouville operator in this way. Now, there's a lot of work in the literature on the study of eigenvalues of the Liouville operator. I haven't spent too much time on this, but some of the papers that I found in the literature where people work out the eigenvalues, no one that sort of explained how they worked out the eigenvalues. So this is, so I decided the easiest is to work out my own way, and this embedding into Rn is basically how I tried to implement the analysis of the eigenvalues of the Liouville operator. It may coincide with what people do in some cases, but probably not all the cases. Okay, so that's what we have. And this Liouville operator, the matrix representation of the Liouville operator, it's a real matrix, and it's not symmetric, and therefore the eigenvalues are either real or else they come in complex conjugate pairs. Okay, right. So now we have the dynamical equation. We can use that to study the expression for the speed of the evolution, or squared velocity of the evolution. And in Euclidean space, that's simply given by the sum of the squares of R dot. Okay. And if we now write the action of the Liouville operator by isolating the unitary term and what you might call a dissipation term, d rho, where d rho is the Limblad term, then the velocity splits into three components. The first part looks almost like the Wigner-Janase skew information in unitary term. Okay, so for unitary theory, the d rho equals 0. So we don't have these two terms. Okay. But of course, we're not working in the Hilbert space, we're working in the Euclidean space. So this is not actually exactly the same as the skew information, because for skew information, the second term is given by h root rho, whereas here we get h rho. So it's a slightly different representation, but that's what we get. So that's the speed of evolution in this Euclidean space arising from unitary evolution associated with Hamiltonian h. But then there's a competition term between h, the unitary evolution, and the displacement term, which is the middle term. And then finally, there's a pure displacement contribution to the evolution speed. But coming back to this representation, basically, the squared velocity amounts to, in R n squared minus 1 in this Euclidean space, the squared velocity amounts to the squared length of the vector, or sum of two vectors, the unitary direction vector and the displacement direction vector. And therefore, if we want to maximize the speed of evolution, this can be done by minimizing the angular separation between the unitary motion and the Limblad motion, or displacement. So that's something one can start to investigate. It's very much an open question how to find, let's say for fixed h, how to find L that would maximize the speed, and so on and so forth. But those questions are going to be relevant to practical implementation of quantum technologies, where one can't, in many cases, one can't avoid the openness of the system. Okay, so incidentally, this the speed of evolution, sorry, going back and forth, the unitary term component of the speed of evolution, we just gave a name, we call that a modified skew information. And so it's essentially representation of the Wigner-Janase skew information in the Euclidean space as opposed to Hilbert space. And that turns out to play a role here when we start addressing the question about the loss of purity of the state. Okay, so if you have an open system dynamics, every time you keep tracing out the environment, which means you keep lose information continuously. Okay, so the state becomes more and more mixed. Okay, or at least the degree of mixture of the state cannot increase. It can stay the same if you have unitary motion, or it will decrease, but not opposite can happen. So that's just life one has to live with in the context of open system, and therefore it's useful to sort of isolate this decay component and everything else in the dynamics. And I have a little bit more to say about that. But looking at the speed of the reduction of the purity, so the purity is defined by trace of rho squared. Okay, so if rho is pure state, rho squared equals rho, and therefore the trace equals 1. But if you have mixed state, rho squared is not rho, and you get a number less than 1. So how rapidly does the purity decrease? And so we call that V sub r, that's the velocity in the radial component, which gives you the reduction of the purity. And it turns out that it's given, apart from the overall weighting factor in the denominator, it's given by the sum of this modified skew information. So this guy determines the decay into states, the rate of decay into states with more ignorance. Okay. So, so that's the expression for the speed, and now we can look at one or two examples where, in fact, I'm going to look at just two examples. So the first example is where h is given by, let's take the 2 by 2 case. In fact, both examples are 2 by 2 case. So h is given by sigma z, and the Limblad operator is also given by sigma z. So this gives you what sometimes people call decoherence. So the density matrix gets diagonalized in the sigma z basis, and it can sort of describe measurement of the spin z components. Okay, and in this case, if you work out the squared velocity, then you get some constant times exponentially decaying factor. So it's just simply decaying exponentially. Okay, so that's not so interesting, but already something interesting happens if we look at the case where h is sigma x, but L is given by sigma z. So they don't commute. Okay, and we can think of this as perhaps the simplest PT symmetric open quantum system. Okay, and the lambda matrix one can work out explicitly, and it's given by this matrix down here, and therefore the Louvre operator, which is 4 by 4 matrix, so it's lambda plus the B vector we had earlier. So that matrix has got 4 eigenvalues. They're given by 0, minus 2 gamma, and then minus 2 gamma plus minus square root of gamma squared minus G squared. So now it's looking sort of familiar. And in the region of unbroken PT symmetry, G is going to be greater than gamma. Okay, now that may seem slightly counterintuitive, so I have to backtrack slightly, sorry. And let me just find the Louvre equation, sorry. Here it is. So we have this equation, and you can, if you like, have an complex number I on the right-hand side to make it look more like Schrodinger's equation, but we don't. Okay, so the point is rho dot is L times rho, and if you want to make it look more like Schrodinger's equation, you could insert I, but we are using the representation where there is no I, okay? And therefore, the breakdown of PT symmetry, things come in reverse direction, so to speak. So the region of unbroken PT symmetry is where complex numbers emerge, because there's no complex number here in our equation, okay? So that's when G is greater than gamma, and then eigenvalues, the first two eigenvalues remain real, but the last two eigenvalues become complex conjugate pairs, okay? And then the symmetry gets broken at the exception point where G equals gamma. And when G is less than gamma, then all eigenvalues are real. And that's in the broken phase where real eigenvalues means decay, pure decay. Other question? Or, no? Okay, so that's just the convention we are working with. Okay, so we expect to see different behaviors in the dynamics depending on whether the PT symmetry is broken or not. And indeed, it's straightforward to work out the solution to the dynamical equation. The Rx, Ry, and Rz is given in this representation where omega is this number. So in the unbroken region where G is greater than gamma, omega is real. So you get an oscillation, okay? But when omega becomes imaginary in a broken phase, then cosine and sine becomes hyperbolic cosine and I times hyperbolic sine. So you get a rather different behavior altogether, okay? So that's what we find. And I just close off by showing, I'm so sorry, yeah, one other comment before I show you the plots. Okay, so I'm going to show you the plot for the behavior of the velocity or squared velocity. Now I already mentioned about V sub r, which is the velocity component of the velocity where your purity is reducing, so the radial component. And then the remaining velocity, so V squared minus VR squared, we call that Vt squared, that's the tangential component of the speed. Okay? And in some sense, that's the more interesting quantity to explore. So we looked at an example where the initial state is in a spin-up eigenstate. So in this case, the initial state is an eigenstate of the Limblad operator, which is sigma z, and therefore at time 0, the reduction of the purity, the speed of the reduction of the purity is 0. But of course, the Hamiltonian is going to move the state, so that's going to change. Okay? And so what we find is that in the unbroken phase, you see there's always an overall exponential decay. So what's of interest is what remains when you take out the decay. So in the unbroken phase, the velocity or acceleration or the state itself, they all exhibit oscillations, which is superimposed with a decay, okay? And in particular, VR oscillates periodically with a given period, and you can I'll show you the picture in a moment. Whereas in a broken phase, there's nothing interesting happens. Things just decay. Very much like in the case of various experiments being implemented for PT symmetric system in a classical context. So you get very similar behavior in the context of open systems. So here, is that, oh, sorry. Yeah, sorry. So that's the velocity of this of the evolution. So the black one is the unbroken phase. So you have this oscillation, and then at the critical point, that's the blue dot, and then in the broken phase you get the red curve. So the speed reduces very rapidly and then lingers for a long time. Okay. And this is the radial component, the reduction speed of the purity, essentially. And in the unbroken phase, it oscillates, but the height will gradually get damped owing to the exponential damping effect. Whereas in a critical level, you get a sharp peak and then just decays, and similar behavior in a broken phase, but lasting for much longer. So that's the red one down here. Okay. And finally, looking at the tangential component, and that's the interesting one because we're interested in how far you can move the state without decaying too much. Okay, so that's the tangential component. And we find that the tangential component of the speed, apart from the fact that it oscillates, it's significantly higher than the broken phase. It's higher in the unbroken phase as compared to critical or the broken phase. So the sustaining the PT symmetry, you can move the state much further, so to speak. So that's basically end of my slides. I'm very happy to take questions. Thank you for your attention.
Thank you, Dorje.
Thank you very much.
Any questions? If you just unmute yourself and ask the question.
Yes, I have some questions.
Go ahead.
Maybe I can start also my video. Okay, hi. So thank you for the talk, very interesting. And so I have a couple of questions. So if they are too much, then stop me so other people can ask.
Yeah, who am I speaking to? Sorry.
I am Federico from Palermo, PhD student.
Oh, yeah, yes, yeah.
Fabio Bagarello.
No, I see you. Yeah, sorry.
Okay, so in one of the first slides, I read a sentence that I didn't really understand. So you said something like, every open system is in a certain sense PT symmetric. And what do you mean exactly by that?
Right. So, for a PT symmetric operator, the eigenvalues are always either real or they come in complex conjugate pairs. And it is known, I don't actually know who, I mean, I know Carl Bender has done some work on this. Perhaps Michael Berry also did some work. Anyway, it is known that such an operator, you can always find relevant parity and time reversal symmetry associated with such an operator. And therefore, such an operator can always be viewed as PT symmetric.
Okay, so in the sense that if you build like a matrix that represents the Lindblad operator, then it always has either real or complex conjugate pairs, right?
Yes, yes,
okay.
Yes.
Yeah. And
not much work beyond what I said has been done to my knowledge. So what would be interesting is then to more precisely identify for generic open systems what's the role of the parity and so on and so forth. I think that would be an interesting question, but I don't know the answer to that question.
Yeah, there are many. When you were saying that, I was thinking about some recent papers by Franco Nori and other people about eigenvalues of the Liouvillean, and maybe you know them. I don't know, but there is something about this, I think.
Yeah. I know some of the papers. Recently, I had a lengthy paper where they sort of reproduced the result in here using different language, but maybe there's a follow-up paper where they look at open system more closely. Yeah, I will try to look it up. Thank you.
Yeah, and then I think in slide 11, you wrote the formula for the velocity in the general form. Yeah, okay, so here it seems like the velocity squared is complex because there is minus 2i, right? But
no, because you have a commutator. Commutator is defined I mean, I is coupled to the commutator.
Ah, okay. Okay. Yeah. Sorry. This was just
Yeah.
yeah, something that I missed.
Yeah.
Okay.
So no, it's not. Yeah, it's real.
And then maybe if I can, just the last question. In one of the last plots that you showed, where you had the velocity versus time, the previous one. I was wondering, is this transition at the exceptional point like a really sharp change of behavior, or because from these three instances, it could be also like a smooth transition? But I was wondering if you looked at other values of gamma and g.
Right. So for the velocity, it's not very sharp.
Okay.
So it's very smooth. But the other quantities you can examine, and then it becomes sharper. So it depends on what quantity one is looking at. But in the case of velocity, it's not very sharp.
Okay.
Yeah.
Thank you.
More questions?
I have one question. Someone heard me? I am Jose Cervero.
Hi.
All right. I was wondering whether the Lindblad operator is uniquely defined always for any Hamiltonian, or you need additional information, because you have been given, let me see, one of the transparencies, you have given the Lindblad operator like something different. So it's an input, or it can be uniquely defined.
Right. So, I mean, just as much as Hamiltonian, you can choose, depending on the system you have. The Lindblad operator also you can choose by choosing the way in which the system interacts with the environment. So,
Okay.
so you have the choice.
So, the different choices change your the things that you have found. I mean, the results.
Yeah. So we looked at a simple example where
I was only worried about if this formalism is absolutely can be absolutely demonstrated, or you need some additional information from the open system. See what I mean?
Well, not quite. So demonstrate in the sense of experiment, or?
Yes.
Well, yes.
Yeah.
Certainly, yes.
All right.
Yes. Yeah, that's the answer. I mean.
Sorry?
So the answer is yes.
Yeah, okay. I understood.
Yeah, okay.
No questions.
Okay.
Wasim, you had a question. Do you want to ask this loud? You put it in the chat.
Sure, yes. Just related to Federico's question on the final plots, in terms of understanding the speed of decay. So for the tangential velocity, how does that vary for, let's say, at a fixed time and a fixed value of gamma? As we vary g and go through the critical point, how does that vary? If that makes sense.
Sure thing. Well, say that again. Sorry.
Yeah. So so let's say we take a fixed value of t over tau here.
Yeah.
Let's say that's 1.
Yeah.
And so we fix that, and we fix gamma,
Mm.
but we now just vary g from a high level through the critical point to 0.
Mm.
Is there a sharp drop off at the critical point, or is it quite smooth? I.e., how sensitive are we really to g?
Yeah, so this, yeah, as you said, it's related to the earlier question, and one can easily plot the answer to your question. That particular question I haven't plotted, but I think it's reasonably smooth. So the velocity doesn't tell you very much about the transition, apart from whether it's oscillatory or not. Okay, But there are other observables you can examine where you get a more critical behavior as you change the regime. Okay.
Thank you very much.
So the velocity doesn't change very sharply. It's just behavior changes. So the behavior of the velocity changes sharply, but the value of the velocity is fairly smooth.
Can I ask that same question?
Yes.
If you're in the G greater than gamma phase and you start moving G towards gamma, how do you know that you're coming into a critical point?
I'm so sorry. Can you repeat the question? So,
how would you know that you're coming into a critical point by starting to adjust G so that it gets closer and closer to gamma, but without yet having reached gamma? What is the signal that the critical point is approaching? Is there any of these functions that you're drawing where you actually see that occur?
Not very, as I said, I mean, I suppose if you have fine-grained way of looking at the function, then either the function is monotonic or not. Okay.
Well,
so,
for instance,
yeah.
in a crystal, as you come into the critical point, the correlation length gets larger and larger before you reach the critical point.
Yeah.
So I'm wondering if there's some kind of analogous signal.
Yeah. So that you don't see from the velocity, but just as in the critical phenomena, I mean, here there's no correlation length because it's only one particle. But
obviously, yes.
Yeah. But there is very similar phenomena where you look at the expected time average of time average of the observable and stuff like that. So looking at the velocity, you know whether it's one phase or another by knowing whether the time decay of the speed is monotonic or not.
Oh,
okay. Yeah. But if you want to explore more dramatic behavior of the two phases, then you have to start working out the time average of observable quantities. So for example, the time average of sigma z. And then you find different behavior in the two phases.
Okay.
Yep.
Good.
Yep.
I have a question.
Ali, go ahead.
Yes. So you kind of embed the space of all mixed states inside Euclidean space.
Yep.
Right? Now, what happens if you take the induced metric of this embedding and compare it with the Fubini study metric on the space of pure states? Because space of pure states are a kind of boundary of the space of mixed states.
Yeah. That's right. This is very complicated. I mean, that's a very good question, but it's very complicated. So the point is the embedding, so the sphere up here is where the pure state is mapped onto. And there's a theorem in geometry due to Kobayashi from the 70s that this is the minimum immersion of the Fubini-Study manifold in the Euclidean space. Okay, and you can use that fact to work out the Fubini-Study metric by looking at the induced metric coming from the ambient, not the ambient Fubini-Study, but the ambient Euclidean metric. Okay, and then you can get the Fubini-Study metric. And in fact, the first time that calculation was done was back in the 1890s by some obscure French mathematician. So that can be done. But what about mixed state, where there are interior points, but it's a manifold with boundaries, many layers of boundaries. So, you know, if there's only one boundary, then yes, it becomes one of these symmetric homogeneous domain, and then it'll be a Kähler manifold. But since there's layers of different boundaries, things get very, very complicated. So I don't think it's so easy to work out the metric in this way. Yeah.
So I was asking because is it compatible with the Fubini step metric?
Well,
You
it certainly is
put in-
compatible if you just take the boundary, yes. As I said, this embedding precisely is the minimum embedding of the Fubini-Study metric. And therefore, if you take the boundary on the sphere, then the metric induced by the Euclidean norm is the Fubini-Study. So it is compatible.
I meant that compatibility between the metric on the space of mixed states and the Fubini study. See, because it's I mean, one holds on the boundary and one holds inside. So what happens if you take the limit? I mean,
Well, I think there won't be any limit. I mean, just take imagine you have a Poincare half plane. You know, the boundary is a straight line, right? And then the metric on the other side is the hyperbolic metric. I mean, no, you don't recover one from the other. It's sort of distinct. And that's precisely what's happening here. So you can examine the metric of the interior or examine the metric of the boundary, but they don't, you know, you don't get one from the other so easily.
no.
More questions?
It's hi, it's Wasim here again. Just one more question. I hope it's well posed. Earlier, you stated or described some equivalence between PT symmetric systems and a system described by a Lindblad equation. Obviously, there are some assumptions that go into quantum systems that can be described by the Lindblad equation in terms of the type of bath you have, and I believe the Markovian process and so on. So, if we think of the two systems, could you comment on whether the PT symmetric systems are a bigger class and a subset of those can be described by Lindblad, or is it a one-to-one correspondence, or is the Lindblad, are the systems explained in Lindblad form bigger than PT symmetric? If you could just help me with that and comment on that, that'd be great.
Okay. Right. So I guess the statement I have on the slides perhaps is slightly inaccurate. The point is, I mean, every open in this sense. And you're right that not every open system can be written in this form. For example, if you have, as you said, non-Markovian dynamics, or if the density matrix doesn't satisfy differential equation, then you have what is called the Claus operator and so on and so forth. So you get slightly different characterization for the dynamics. But this already exhausts very large class of interesting situations. And for this class of open systems, you can regard them as being PT symmetric, okay? And in which way they will correspond, where does the physics come in, where that is an interesting research topic. You can explore that. And that's pretty much open. I think not much has been done. I know that the group in Stuttgart, Holger Katarios and Gunther Wunner, they have been looking at this Lindblad type dynamics in the context of Bose-Einstein condensate. So your system is part of the potential there, and then you have the environment, and then you have a bunch of particles here, and you can adjust the potential in such a way that you can have this on average PT symmetric system. Okay, so the tunneling of the particle, you can control the rate of the tunneling, and you can also control the rate of tunneling of the particle going out, and in that way you get, you can't have a precise PT symmetry as I said earlier, but you can have, in a meaningful way, on average, PT symmetric quantum system, and they do explore the Lindblad type dynamics for a system of that type. So that's a good example of where interesting physics can be brought into the picture. And I think my hope is that many, many other interesting systems will be explored in a purely quantum regime.
Thank
in
you.
in an open context.
Thank you very much.
No more questions? Anyone else?
I can make a comment. This Liouvillean, you get complex conjugate pairs of eigenvalues because you have a matrix which is real, right?
Mhm.
So really it's not PT symmetric, it is T symmetric. It commutes with complex conjugation. And that's why you're getting this complex conjugate pairs. So every matrix which is real will have real or complex conjugate pair of eigenvalues.
Right. And we have the secular equation, which is also real.
Yeah.
And there is a work, I think there are several papers, perhaps Carl can enlighten me, but I think there's a paper by Bender and Berry, and also other papers by Bender, where they have explored the link between PT symmetry and every operator having whose eigenvalue equation is secular. Secular equation is real. So that's
if I
connection that I had in mind.
I can just comment. I talked about this a few weeks ago, and I proved a paper where if a system has complex conjugate pairs, then there is an antilinear symmetry of some description, not necessarily PT. And the example Ali just gave, the antilinear symmetry is actually complex conjugation. But there's always some antilinear symmetry. And it goes both ways. Antilinear symmetry implies eigenvalues real or in complex pairs. Eigenvalues real or in complex pairs implies the existence of an antilinear symmetry. And PT is the sort of classic example of such an antilinear symmetry.
Now, this is what I had proven in 2002. And the precise statement is that there is an antilinear symmetry which squares to 1. This if and non-live.
Okay.
So PT is an example and T is also an example. You can always introduce P and T operators separately for such situations. But the point is that this new T and P operators need not commute. This is all in the 2002 papers.
Is that your series in JMath Phys?
Yes.
Oh, okay. Yeah, those are the ones I quote all the time.
Yeah.
Yes. I just didn't remember the year. Sure. I believe I've given you full credit for everything in your papers.
Thank you.
Any more questions? No more questions? Well, then let's thank Dorje again. Thank you very much.
Thank you very much.
And
Very
we
much.
meet again in 2 weeks. The next speaker is Savannah.
Good.
Bye, everybody.
Bye.
Thank you very much. Bye bye.
Andreas, thank you. Dorje,
Thank you very much, everyone.
nicely done, Dorje.
Thank you.
Good to see you, Dorje.
Yes, how are you, Carl?